This is problem 3-120.m. It's on page 171. We'll work it as an example problem for stress concentration. And I'm going to need some calculator help. I apologize, I did not write this out before coming to class. I've got to write it out still. But I will write it out and make a PDF of it and post it for you guys. So if you want to copy it down, you're welcome to, but there's really no need. You will have a copy of it eventually. Let me read it. Figure P3-120 shows a circular shaft subjected to a repeated axial tensile load of 25 kilonewtons. The shaft is made from AISI 4140 OQT 1100 steel. Determine the design factor at the hole and at the fillet. So if you have your book, turn to page 172 at least and look at the picture. And I'll go ahead and draw it up here, I guess, because we'll have to refer to it quite a bit. So it's a round section. Has not only a fillet to transition in size, but it has a hole. And there are dimensions given. This section is 25 millimeter diameter. The hole's in the center and is 10 millimeters in diameter. The radius of the fillet is 2 millimeters, and the diameter of the smaller section is 20 millimeters. So there's going to be stress concentration here, there's going to be stress concentration here. The question is, what's the design factor? In other words, how close is this thing to failing at those 2 points? Why would we care? Well, the one with the lower factor is probably where the thing's going to fail, right? So we'd like to know, is it going to fail at the fillet, or would it ultimately fail at the hole? All right, so let's start off getting the stress concentration factors, because you realize we're going to need that, right? So let's just go do it. So go to the back of your book, go to the stress concentration factors. Let me make just a couple notes. Go back to appendix 22 and I'll write down some more information. The force is 25 kilonewtons, and it's 4140 OQ T1100. That way we don't forget what material it is. Okay, so let's go to the stress concentration factors and find out the value of K's. Now, which charts do you think we ought to be on? This time it's not a trick question. 22-2, I agree. For which one, the hole or the fillet? The fillet, good. So let's go to page 725, which is appendix 22-2, and try to read off a factor. Now notice the stress concentration factors are all on the y-axis, but we have to find our place on the x-axis and which curve. The x-axis is the ratio of the radius of the fillet to the smaller diameter. Notice that this is little d, okay? So we need r over d. So somebody grab your calculator and tell me what never mind. There we go. I can do that. I can math. All right, what curve are we on? Well, notice this is capital D, okay? So capital D over little d tells us what curve that we're on. So 25 over 20. Well, let's see, that'd be 2.5 cut in half, so I can do that one too. I think I can do it. Yeah, 1.25. Yeah, that's right. A minute, I thought I had the decimal place off, but that should be okay. All right? So, do you see a curve that's marked 1.25? No. Neither do I. What do you see that's closest? 1.2. 1.2. So we're going to go slightly to the right of curve 1.2 and do our best. I call it visual interpolation. Another way of talking about it is called a sophisticated wild guess. Okay? All right. So, on the x-axis, we're at 0.1. And on the curve, we're going to go up to 1.2 and add a little bit to it. What do you think is a reasonable value for the stress concentration factor? 1.75. Well, let me see. Do I agree with that? 1.75 is a little bit below the line, isn't it? 1.75 would be the line in between 1.7 and 1.8.
1.85?
1.85 I think might be a little high. We could go with 1.8, but if you're at 0.1 on the x-axis, then notice that the line for 1.2 is between 1.75 and 1.8. You see that? So somewhere between 1.75 and 1.8, even 1.8 is probably okay. Now if I look, there's a curve of 2.0, so I could try to count how many squares there are from 1.2 to 2.0 and, you know, become very mathematical with it. I'm not going to bother. I'm just going to say the stress concentration factor, which by the way is approximate anyway, is about 1.8. Okay? So that's the stress concentration factor for this. So this is for the fillet only. What does that mean? Well, that means if I calculate the stress in this area, I need to multiply it by about 1.8 to estimate the peak stress. What stress would I calculate? Would I calculate the stress in this member and multiply it by 1.8, or this stress times 1.8? The smaller one, right? Because the fillet is part of both, but it's going to concentrate stress the most where the stress is already highest, right? That's where it's going to have the worst effect. Okay, we'll get to that in just a minute. For now, let's finish off the stress concentration factors. So what other appendix number do you think we should use here?
22-5.
How much?
22-5.
22-5, I agree. Why not 22-4?
Because it's a flat plate, you know,
Sorry.
we're using cylinders.
There you go. They're both holes, but 22-4 is a flat plate, 22-5 is a cylinder. So on page 728, appendix 22-5, well, we need the same kind of stuff, right? We need the diameter, small diameter, which in this case is the diameter of the hole. Now don't get confused here. This little d is different than this little d, okay? We're talking about this part now. All right? So we need the diameter here over the diameter of the section, the larger section. So d over d then would be 10 over 25. Can't think of a quick way to do that one in my head. How much is it?
0.4.
0.4, thank you. Okay, so that tells us where we're at on the x-axis. But now we've got a family of curves A, B, and C. Well, which one are we dealing with here? Well, let's see. Notice curve A is for tension. Curve B is for bending. Curve C is for torsion. In our case, we're talking about tension. So we're on curve A. Does everybody understand that? Any questions on that? All right. I don't know yet what you guys will struggle with, so I don't know when to go fast or slow. We'll find out. Okay, curve A at 40% on the x-axis. Well, they would choose a nice area where everything's crossing. Yeah, let's see. Looks like.
5.
Sorry?
5.
Yeah, it looks like about 5 or so. Why do they call it KTG? No, KTG is based on the nominal stress in a round bar without a hole gross section. That's a really good thing. I'll explain why in a minute. Now, it's a little bit above 5, but again, this is approximate. I'm going to read it off close enough to 5. Okay, so let's put them over here so we can keep track of them. KTG equals 5.0. And over here, KT equals 1.8. Okay? Why do they tell us the gross section? What difference would it make? Well, the reason is because if you look at the cross section where the hole's been drilled out, you basically don't have this area anymore. If you want to calculate that area, it's not trivial. Well, depending on what your definition of trivial is, but it would be easy to subtract out a rectangle, right? But what about this other area over here and over here? You got to figure that out. The only way I could think of doing it was to make a center mark here, calculate the area, say that area, because it's a segment. Okay, and then this is a triangle. Do a bunch of geometry work. Actually, it started up SolidWorks because I didn't realize they had it based on the bulk section, or what do they call it, the gross section. I was going to let SolidWorks do the heavy lifting for me in geometry. So we don't need SolidWorks. So it's a good thing that it's based on the stress in the gross area, because now all we have to do is calculate the stress over here, and that'll be fine, where there is no hole. Does that make sense? There is just a circle. Okay, the area is just a circle. All right. So let's calculate the stresses in each of these sections. So let's see, the stress at the fillet, let's just put a subscript F so we know which part. Better yet, let's do it this way. For the fillet section, the stress is just going to be force per area, right? So force over area. We're interested in something here, basically. So the force is 25 kilonewtons, and then the area would be pi times the diameter, 20 millimeters, squared over 4. Okay? That's going to be the same thing as, let's see, 400 over pi over 20 squared. And the units would be kilonewtons per millimeter squared. Do you guys remember what kilonewtons per millimeter squared turned out to be? If you don't remember, you can figure it out. Should we go through the process of figuring it out? Probably. I see a lot of blank looks. Kilonewton per millimeter squared. You expect, since this is force per area, to get something like pascals, right? Because a newton per meter squared is a pascal. So let's see, so this is the same thing as 1,000, let me write it as 10 to the third, newtons per millimeter squared. Let me multiply that by 1,000 millimeters per 1 meter, but I have to do that twice, so square it. And that will take care of the square millimeters. You know, you can all do this in your heads, right? Because 1,000 squared is just 1,000,000, which is just a million, just add the zeros. So that's 10 to the 6th, right? This whole thing. 10 to the 6th plus 10 to the 3rd is 10 to the 9th. Newtons per, the square works on the unit as well, so this, by the way, is a pascal. Okay, what would we call 10 to the 9th pascals? Well, let's see, kilo is 1,000, mega is 1,000,000, giga is 10 to the 9th. Okay, so this is the same thing as a gigapascal. That's something worth committing to memory for this class, is that a kilonewton per millimeter square is a gigapascal. So the point here is that we end up with gigapascals. All right, so now throw this into your calculator if you would. 100 over pi over 200 squared is how much? I need a calculator help, please. 200 squared is 400, so a quarter divided by pi is how much? It's the same thing. And the bystander effect takes hold. You guys know about the bystander effect, right? Where something's going on and everyone expects someone else to do something about it.
I have 108.
108?
0.08.
Anyone second that? Thank you. And I assume that's rounded off because pi is not rational. So that's fine. So 0.08 gigapascals. All right, so there's now that's the nominal stress, right? This is just the nominal stress in this section. We have to multiply that by the stress concentration factor. So the maximum stress at the fillet then would be 1.8 times the 0.08 gigapascal. So if you still have that number in your calculator, just multiply it by 1.8. What do we end up with? How much? 0.14 gigapascals. Okay, so there's the effective stress. So let's write it down here. So the maximum stress at the fillet, 0.14 gigapascals. We still don't know how close we are to the material failing, but we do know that's the strength. Or that's the stress, excuse me. So now let's go for the hole in the larger section. I think I have a mark over here. I need to not go past it. Okay, so the larger section, the hole, we need to calculate the stress, and it's just, again, force over area. It's pretty straightforward, 25 kilonewtons divided by the area, still pi. Diameter is the only thing that changes. So this is 100 kilonewton, well, 100 over pi, 25 squared gigapascals. course, if you still had the 100 over pi over 20 squared in your calculator, you can come up with the stress here pretty easily. But if not, just plug that in your calculator, and what do you come up with?
0.5.
105, thank you. Anyone second that?
I do.
I don't mean to be insulting by asking that, I just want to make sure our solution comes out reasonably close to right. So now the maximum stress is just the stress concentration factor, which is 5, times the 0.05 gigapascals. I think I can do that one in my head, 0.25 gigapascals, right? So there's the stress around the hole. But this is not the question. The question is, what's the design factor, or what's the factor of safety in this problem? All right. Well, to figure that out, we have to know something. We have to know something about the material. The material is 4140. If you go back to the back of your book and look up 4140 in the material properties, what you'll find is that 4140 has various percents elongation depending on the treatment. What do you notice about all the percents of elongations? I'm on page 714. They're all above a certain magic number. They're all above 5%. What does that tell you about 4140? It is a ductile material, that's right. So since it's ductile, then what we need to do is use sorry, before we turn away from that, let's get a couple of things. Let's grab the, we don't know which one we need yet, so we'll grab both the yield strength and the ultimate strength. The yield strength 4140, OQT 1100. The ultimate strength is 1014 megapascals, which is 1.01 gigapascals. So let's see, ultimate strength 1.01, I guess, if we want it. Gigapascals. Yield strength looks like it's 0.903 gigapascals. Everybody see where I got those? Did I get the right numbers? Okay, page 714. Look up 4140. It's almost the last alloy. And then look up OQT 1100, it's a particular row within that alloy. And then you can just go over on that same row and read off the 1014 and the 903. Okay, good question. Anybody else? Okay. All right. So there's the yield strength and the ultimate strength. Now, which one should we use? Well, being a ductile material, go back to chapter 3. And there was a table I said you should commit to memory or mark. Page 119, table 3.2. Notice in this table, we're in ductile material, right? So we're in the left-hand column. But we have a repeated load. They told us that the load is cyclical in nature. It varies over time. It's repeated. It's applied, released, applied, released. And so notice what they're using for their design stress is the ultimate strength. See that? In fact, they've got a factor of 8. Wait a second, I thought we were trying to find the factor. Well, I just didn't know whether we were supposed to use the yield strength or the ultimate strength. And this tells me that we needed to use the ultimate strength. So this is the one we care about. Does that make sense? We don't care about this one because it's a repeated load. This is the procedure we're supposed to use. Okay. So, how do we calculate? Well, you notice that what they've done here is they've said that the design stress is the ultimate strength over 8. Well, 8 is just the design factor. If we're supposed to design or solve for the design factor, then what we need to do is take the ultimate strength and divide it by the actual stress. Okay? So the actual stress that we have in these two sections is different, right? We've calculated them here and here. So the design factor for the fillet would be the ultimate strength, 1.014 gigapascals, divided by the design stress. We're at the fillet, so that's 0.14 gigapascals. Okay, so plug that in your calculator, please, and what do we get? 2. Now, it's recommended for ductile materials that under repeated loading, that the design factor be 8. Is this design good enough? No, because the factor is not as high as it should be. How about at the hole? Well, you can already tell that's going to be worse, right? Because the load there is even higher. But let's go ahead and calculate it. So the design factor for the hole, I guess I'll use H for that, is 1.014 gigapascals divided by 0.25 gigapascals. So what is a quarter of 1 or so? It's going to be about 4.1. No, I said a quarter of. I meant the other way around. 4.1? 4.1, thanks. So the design factor is obviously even worse back here. Where would it fail first?
No.
Right there, at the hole. Is that a little bit surprising? Maybe, maybe not. Notice it really depends on how big the hole is by comparison to the shaft versus how big the radius here is by comparison to the smaller section. And apparently this radius here is not all that small by comparison to the diameter, whereas this hole takes a big chunk out of it. Okay. Questions, comments?
So it'll fail at the hole first because it's got the smaller factor?
Yeah, you can say it two different ways. It'll fail at the hole first because it has the higher stress, or you could say because it has the smaller factor of safety. Good question. Anything else?
You had mentioned you pulled up SolidWorks to show us.
Oh, what was I going to show you in SolidWorks? I'll show you that off the video. It's not interesting for the video. I'll repeat why it's important. This stress concentration factor they gave us is really nice because we don't have to calculate the cross-sectional area and remove the area that hole removed. It makes it really nice. Okay. Anything else? All right.